Hi everyone. In this video lesson, we're going to do a little bit more with conservation of momentum. We're not actually learning anything, any new concepts in this lesson. We're just tying a few concepts together with a couple of example problems. I don't anticipate it should be a terribly long lesson, so let's get started. So in our first problem, and maybe you can visualize yourself in this kind of problem, like maybe swimming in a pool. Everybody loves like trying to stand up on some kind of floating device, but it always kind of shoots out from underneath us. At least I think that's fun. But here we have a vacationer with a certain mass and is standing on a raft. So in the initial diagram here, you can see they're all just at rest. But then the vacationer starts walking towards one end of the raft. And so from someone on the beach or someone in the water, so from the water's perspective, we see that vacationer walking at 2.3 meters per second to the right. And if we think about it, we know this from personal experience, maybe even from like standing on a skateboard, but if you start walking one way, your skateboard or in here the raft is going to shoot out the other way. And what we'd like to find out here is with what speed is the raft going to move to the left at. Now, this question could also be thought of as not exactly a collision, because we've been analyzing collisions. You could think of this example as an explosion, where two things are kind of together and then they kind of fly apart, and one goes one way and one goes the other way. So the total momentum before is 0. And so the momentum afterwards has to be 0 too. So the momentum of the person walking one way has to match the momentum of the raft going the other way. So that's the premise for the question. So it is a new kind of collision, which we're going to call an explosion. We're also going to tie in some relative velocity here as well. So begin with our solution. So we're going to start off with just setting up conservation of momentum. So M1, that's our person, V1I plus M2 V2I equals M1 V1F plus M2 V2F, kind of our classic way of setting up a collision problem. In an explosion, well, usually what happens in an explosion is the bodies that are together are at rest. And so here we have that, right? The raft and the person are at rest. The total momentum is 0. And we can solve for V1, we're solving for V2F because we're saying V1F is the person's final speed. So just solving this for V2F, we get negative M1 V1F, moving it left, and we'll divide by M2. And I don't want to generalize all problems are the same, but this setup is generally true for any explosion question where two things are just going off in opposite directions. So we have the mass of the person, 75. And notice the negative sign, that's okay because if we're treating right as positive, the raft will be moving to the left, right? V1F, we're told, is 2.3 meters per second. And the mass of the raft, 55. So let's do that, and then I just have a couple of talking points. So about negative 3.1 meters per second, or that's 3.1 meters per second to the left. As we think about it, what could make this V2F higher? What would cause the raft to actually move faster? Well, if you increased the mass of the person or decreased the mass of the raft, that would increase this final speed. So it makes sense in an explosion, the piece that has the lower mass will be moving at the faster speed. So if you can see, the person was moving at 2.3, the raft moving at 3.1, and that always happens. The lower mass has the higher speed because the momentums have to match, right? So now that we found the speed of so this is the speed that, if I was sitting on the beach, I would see the person walking right at 2.3 meters per second. I would see the raft moving left at 3.1 meters per second. But say, what would the person see? So let's talk about the relative velocity of the man relative to the raft. Conversely, when we find this, we're also finding the relative velocity of the raft with respect to the man. They'd just be in different directions. So let's set up our chain of subscripts, right? Where we want to find the velocity of the man with respect to the raft. So we need the velocity of the man with respect to the water plus the velocity of the water with respect to the raft. Now we have those things, right? Well, I mean, we have the velocity of the man with respect to the water. It was given in the question, right? And we actually found the velocity of the raft with respect to the water. So why don't we just rewrite this as minus VRW? And then we have both of these things, right? If we choose right to be positive, the velocity of the man with respect to the water was 2.3 meters per second to the right. And the velocity of the raft with respect to the water was 3.1 meters per second to the left. And then whichever way you slice it, whichever way you like to do these problems, so I can change that to plus 3.1 meters per second to the right. That's 5.4 meters per second to the right. So the raft would see the raft would say, hey, I'm not moving. This person is walking off of me at a speed of 5.4 meters per second to the right. And the person will be saying, hey, I'm standing still, and this raft is shooting out from underneath me at 5.4 meters per second to the left. So not an overwhelmingly complex problem in terms of the math, but we looked at what we call an explosion question. Talked about how the masses affect the final speeds, and then we just tied in some relative velocity to that. Let's look at our second example. Our second example combines our knowledge of conservation of momentum and conservation of energy into a single problem. So what is illustrated here is a ballistic pendulum. So the idea is you fire a bullet where you know the mass and velocity of the bullet, and you fire it into what we call this ballistics pendulum, because it's going to embed itself in the big block here. And then when it does that, momentum is going to cause the pendulum to swing. And what you can do is, if given the speed of the bullet, you can try to predict what the height of the pendulum would be. And conversely, given the height of the ballistics pendulum, you can actually work backwards and determine how fast a bullet is shot at. So this can be useful in like forensics analysis if you kind of err into that kind of thing. But the big idea is we got to kind of do problems like this in two stages. When there's a collision, we have to analyze we have the initial speeds right before the collision and right after. And then we'll have to analyze the using conservation energy, how high will the ballistics pendulum get? Because momentum is not conserved when other forces are acting on the system, right? So once the pendulum starts to swing, it's going to slow down. Eventually, its momentum will be zero. It's not violating conservation of momentum. Momentum is conserved before the collision and right after the collision. But after that, all bets are off. We'll need to use conservation energy to see how high it swings. So having set up the problem, let's do it. So we have a bullet impacting this big wooden block, and it hits at 500 meters per second. And we're going to say the bullet has a mass of 50 grams, and the big block has a mass of 10 kilograms. So what we want to do first is analyze what's the speed of the bullet block, like right after the collision. So I might say it this way, just to save some space. Find VF of m plus m. So that's when the bullet embeds itself on the block. That's going to be their combined mass after the collision. So let's set up our conservation momentum equation. So we have little m for the bullet, and I'm going to use little v for this one. I'm just going to play around subscripts. Plus the mass of the block, and I'll just use a big V, I, for the initial speed, big V, for the initial speed of the block. Then afterwards, they combine and have some final speed that we're going to find. Now, whatever you want to use for the speed of the block initially is kind of irrelevant because it's equal to 0, so it just divides out anyway. And this kind of question, we've actually done quite a lot of these. So the final speed combined in this inelastic collision is the mass times the initial speed of the bullet divided by their combined masses. So let's calculate that. So 0.05 kilograms, 500 meters per second, and their combined masses together, 10.05 kilograms. So what we're expecting is because the mass of the block is so much bigger compared to the bullet, that the combined speed of the block and the the bullet should not be too big. Times 500 divided by 10.05. It's actually not too. It's actually pretty significant. So about 2.5 meters per second. That's what I got. Excuse me. All right, so I'm going to go back to my diagram. So now we have that after they've combined, right after the collision, we have this bullet block combo traveling at 2.5 meters per second. And if we treat that center of mass to be h equals 0, now we're just taking all that kinetic energy that the pendulum has, and it's all going to be converted to gravitational potential energy at that point where the pendulum reaches its maximum height. We can find that height. So our step 2 of this problem, we're going to use conservation of energy to find the height it swings at. So you can set it up, if you like setting up E before equals E after. I'm kind of a fan of doing this. Not always, but. So this question does not involve springs at all, so no need to toss that in there. EG2. But initially, our bullet and block are at h equals 0, and when it reaches the maximum height, the speed is 0. And so we have 1/2 in the combined mass. Remember, they're now kind of combined together. And I'm just going to pop in. Remember that they initially they had that final speed coming out of the collision equals m plus m times g times h. And it's actually nice. These masses divide out, and we're solving for h. So h equals vf squared, and we just have to divide by g, divided by 2g. So let's find that. 2.5 squared over 2 times 9.8. Where's my calculator? 2.5 squared divided by 2 divided by 9.8. So I got about 0.32 meters. So that ballistics pendulum is going to swing up, and the bullet block will go up 0.32 meters. Now, as I kind of teased, what's actually most useful is to work backwards in reverse. So, say you had like a murder weapon or a suspected murder weapon, and based on like the victim, and you analyze things, you might say, well, like according to this, the bullet struck the victim at a certain speed, and you want to prove to a court that the murder weapon you have actually could have committed the crime. Well, you could take it to a ballistics lab, and you could fire it at a ballistics pendulum. And you could measure the height that it goes and work backwards and find the speed of the bullet and kind of match the weapon to the crime. So then maybe that's a little bit of a simplified scenario, but not so much actually. could be very useful. So we're going to do that. So now we're going to say, what if our ballistics pendulum swung to a height of 0.4 meters instead? So the speed will be a bit over 500 meters per second, but we're going to actually work backwards, find the speed of the bullet. So we're just going to go in reverse. So this time we'll have to go backwards. We're going to have to use conservation of energy to find the speed right after the collision. So we actually have to find the VF first, what speed they come out with, and then afterwards, then we'll use conservation of momentum to find VI, the speed of the bullet, before the collision. So very similar setup to our previous question. And after all the stuff we've done together, it's not overly hard either. So I'm hoping that you guys are okay if I just set up our problem as we had before. So 1/2 m plus m VF squared, again, it's all kinetic, equals m plus m times GH. We've already developed that and we've already analyzed the situation, so let's just use it. It's just this time we know H, so we don't need the masses. So this time, this time we do know H, we're finding VF. So to solve for VF, multiply up to 2, you get 2GH, and that's VF squared, so we'll square root it. And let's calculate this. So 2 times 9.8, and we said the height is 40 centimeters, or 0.4, and so that gives us our VF. So it's at 19.6 times 0.4, and we root it. Okay, so it comes out a bit faster at 2.8 meters per second. And so now, again, we've already done the setup, right? So initially, the bullet is traveling with its mass of the bullet, with some initial speed, and the big block is not moving, so it has 0 momentum. And then afterwards, the combined mass has a speed of VF. And again, we already did all this setup, right? So we don't really need to rederive everything. And so we can find VI just by isolating in a different way. So we have m plus m VF divided by little m. So that was, the combined mass was 10.05 times 2.8, and the mass of the bullets 0.05. See what we get. 2.8. So you can see about 560 meters per second. So the bullet's going a bit faster. Yeah, that's a really cool application of conservation momentum, collisions, and conservation of energy to do a forensics problem, in this case, a ballistics pendulum. And just as an aside, I have a student who comes back to our department every now and then just to let us know how she's doing. She's studying forensic science, and you'd be very surprised the tools they use to analyze different situations. You'd be surprised at how they connect to things like, grade 12 physics here, or grade 10 right angle triangle trigonometry. The math they use sometimes is complex, but sometimes it's not that complex either, like a problem like this. So I think that's pretty cool. All right, so what's coming up next? So we're going to consider our analysis of one-dimensional collisions to be done. We're going to analyze collisions in 2 dimensions. Since momentum's a vector, and momentum's always conserved, we're going to use the fact that momentum will be conserved in the x direction and the y direction to analyze 3 problems together. And then you'll do a little assessment where you reconstruct a car crash, a simple car crash. And then we'll have this unit on energy momentum kind of wrapped up. So that's it for me for this lesson. Hope you guys are staying well. Have a good day, and we'll see you soon.